All right. Well, I will. Did you guys have a good break? Yeah. More or less. Let us begin with a word of prayer. Don't make me bring back the whistle. All right, here we go. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to guide our steps today. Bless this class, Lord. We pray that we glorify you in what we do. Again, I pray for these students as they work on this course and their other courses this semester, that each day, Lord, they would do their best for your glory, Lord. In your name I pray. Amen. So, somebody had some problem with Wi-Fi somewhere, so I said, fine, here, have another week. And if I give it to one of you guys, I give it to all of you. So there's like some extension on this homework, I think. And most of you have already done this, but I will talk about it yet again. So here the problem is 2 regular 6-sided dice are tossed. Compute the probability that the sum of the pips. I only see this word used in these problems. Nowhere else in society does this terminology exist as far as I've ever seen. Am I wrong? Am I just not enough of a gambler? I don't know. All right, anyway. I just don't have a name for them, so fine, pips. The sum of the pips on the upward faces of the 2 dice is the following. All right, so what do we compute the probability that the sum of the pips on the upward faces of the dice is 2? So you're rolling 2 dice is the main thing, right? How can you get a sum total of 2 from rolling 2 dice? 1 and 1, right? So it's just this case right here. That is it. Oh, wait a minute. Well, that wasn't the question, though, was it? My question here says what? I missed the words down here, right? At least 10. So what does at least 10 include? What's the range of scores for rolling 2 dice? Right? So you can get, if you think about it, you can get from 2 all the way up to 12, right? Now, so if we want at least 10, that's going to include what? Either got 10, 11, or 12, right? How can you get 10? How can you get a roll of 10? 5 and 5, 6 and 4. Um, 6 plus 4, yep. Anything else? 7 plus 3? Not with the usual dice. But there is another one. The other one is 4 plus 6. See, because the order of the, we're talking about 2 separate dice, right? So either get a 4 on the first one and a 6 on the second one, or you get a 6 on the first one and a 4 on the second one, right? Those are separate possibilities. They're, let's see here. It's like this roll right here versus, say, if I can find it, this one right here, right? Both of these are separate rolls of the dice. You see those? You could think of this as being the 6-4 and this as being the 4-6, if you want to think of it. They're separate rolls. I know you can't tell once you roll it, but imagine the dice are colored so you can keep track of which one's which, right? You got a blue dice and a red dice or something, right? Anyway, so 5 plus 5, 6 plus 4, 4 plus 6. I think that's it, though, right? Okay. 11, you can either get from 5 plus 6 or 6 plus 5. And then 12, the only way to get 12 is 6 plus 6, right? So look at it. How many is the number of desired outcomes that we're interested in here? The number is 1, 2, 3, 4, 5, 6. There's 6 of them, right? So the probability of E is the number of the events corresponding to E divided by the total number of events, like possible outcomes, right? Which in this case is 6 over 36, which is 1/6. For this problem has answer 1/6 because there's a 1 out of 6 chance that you're going to roll a number that's 10, 11, or 12. Does this make sense? I hope. All right. Let's work one more, and then we'll leave these problems behind us here. Example number 4 here. If 2 dice are rolled, compute the probability of rolling doubles. Right? So what are the doubles? Let me go back up to the picture here. Let me use the original one for the doubles. Doubles are here. What? There's one here. Right? Here, 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 and here. How many doubles are there? There are 6, right? So the number of doubles divided by the number of total rolls is equal to 6 over, this is so boring, it's again the answer is 1/6. Can't they come up with any other kind of problem? But anyway, there it is. All right, so hey, while we're having this discussion, what would be the probability I roll a 13 with a pair of dice? 0. It's impossible, right? With 2 regular dice. Not like that silly dodecahedral dice they start with, right? How about, what's the probability I roll a 1? 0. Probability is also 0 because you can't roll 1 because you have 2 dice, right? And there's no 0 face on it, so. Are we good? I hope we're good. We're going to move on here. So today, we have moved past probability and counting into the next chapter, which is chapter 13. And, all right, don't fail me now. Come on. I was a little nervous to adjust this thing, I feel like if we make it to the end of the semester, we've done well. All right. So I forgot what lecture number it was, and I haven't looked it up. Could you tell me what lecture number we're on? I've lost track. My bad. Everybody top-hatted? No. Oh, I'm sorry. I forgot. Thought process. I'm done with this homework. I can ignore what Dr. Cook is saying at the moment. Yes. I mean, it's right there. I mean, I wish that we could all ignore Top Hat. I mean, nothing would make me, well, there are many things that would make me happier than that, but it would give me joy to just never open Top Hat in a semester. That is true. Just a second here. I'm seeing which lecture we're to, if I could count. Come on. Come on, Canvas. Load. What week are we in?
8.
Week 8. I guess I need to make an announcement, huh? So you guys know that we're in week 8, right? That'd be good. We had lecture 11 last week, so I guess that means we are in lecture 12. So the Top Hat was, what was it? 1982. All right. Everybody do it now? All right, I got 89 out of 99, so I guess I could count. Let's not do that. Okay, so now we're moving into the discussion of statistics, all right, and So there are two kinds of statistics, as your book introduces. It says there is descriptive statistics, which involves the collection, organization, summarization, presentation, and interpretation of data. Someone in another class I had asked me, isn't it data? And I said, no, it's data. Ever since Star Trek The Next Generation, we have given up on data. It is now data, forever and ever. All right, anyway, so, and then there is also inferential statistics, which interprets and draws conclusions from data. So I think, I mean, you know, I think you've seen both of these. If you search your heart and think about things people have told you in your life, you'll realize you've been immersed in both of these ideas, right? Lots of news stories are nothing more than some dude wrote a paper and it's got these statistical conclusions. Let's talk about it, right? I mean, this is so much of our news. Okay, so we're talking about statistics today. So we're going to really just cover the basics of statistics in this course, all right? So, you know, statistics can be as simple or as complicated as you want it to be. There's research level statistics going on to this day. So one of the things I was interested, so I worked at Liberty from 2008 to 2019, and then I left to work for the Navy for a year. And in that year, I worked in one of these research lab kind of places, and we were studying radar, all right? And a lot of the thinking about radar is statistical, all right? Like weather forecasting is deeply statistical. And anyway, there are still ongoing work trying to understand statistics better and apply it to the world in all kinds of applications. And not just for like corporations and governments and things like that, also in science and engineering. Currently, at the cutting edge of things, there's something called topological data analysis, which tries to merge mathematics, which we've only discovered about 100 years ago, with trying to understand like how you can analyze data. So it's not in this course, right? But I want you to know that statistics, much like pure mathematics, is a subject which is alive. It's not just something that was discovered and applied. It's continually being updated and worked on by experts, of which I am not one. So anyway, so today, let's talk about the mean, the mode, and the mean, the median, and the mode. Listen, so mean is, I don't know, like outside of statistics, most people don't say mean. What do we say instead of mean? Average, right, yeah. So average is what normal people call the mean. So, but we do need to play along with the book, so we're going to call it mean sometimes. And of course, it serves my deeper purpose of confusing the students, so there's always that. But here's the problem. So we have the definition of mean. How do you calculate the average? You add up all of the data that you've got, x1 through xn, all right? And you divide by the total number of data points. This is the average, all right? Now, if you rank the list, right, if you put them in order, x1 less than or equal to x2 less than or equal to x3, less than or equal to xn, rank the list in order, all right? Then the middle number is the median if n is odd. However, if n is even, what you do is you take the average of the middle two, and that defines the median. All right? So this is median. It's the middle number, basically, or the middle of the middle numbers, if it's even. And then the mode is the number which occurs with greatest frequency in the list. All right? So there can be multiple modes. All right? There could be more than one mode, or there could be none. If your list of data is distinct, then there's no mode. All right? So like this one, here's Math 116, because I didn't want to make it, I mean, it's close, but it's not too close to home, right? So this one off. I don't think this exists here, actually. I don't think there's a Math 116. We once titled a math course on a pun, and it was very amusing to me because I watched like arguments about it in the math meeting. So like we introduced this new course, which was Math 130. And the thing is, Math 130 was more simple than like Math 126. And there's generally this idea that as the numbers increase, the difficulty increases. For example, Math 131 is Calculus 1 here, which is a course which is so much harder than this course. Like, I cannot tell you how much harder it is. It is bad relative to this course, okay? You have friends. You do things with them, right? You do things other than homework, right? That's because you're not taking Math 131, all right? Math 131 is an all-encompassing, experience. And then that 132 is Calculus 2. That's much worse. Calculus 2 is one of the hardest courses I took as an undergraduate. It has an irreducible complexity at its core which cannot be removed. You can memorize your way through all kinds of math classes. 132 you cannot do. So this class 130 is like, why are we titling it 130? The other older professors are like, what? But that doesn't make sense. But the reason is that this was math for like aviators. So it's all just a joke about like the C-130 plane. Like that's the whole reason for the for the numbering. So I don't know. It was funny to me. So here we go. We have grades of 70, 72, 78, 80, 85, 85, 91, 96, 100, and 100, right? So the question is, what's the mean? The mean, you add them up. 70 plus 72 plus 78 plus 80 plus 85 plus 85 plus 96, 91 plus 96 plus 100 plus 100. That adds up to 857. Divide that by 10, you get 85.7. The average, or the mean, of the grades is 85.7. All right? The median, this is 10, right? So this is even. So we actually have to take the average of the middle two numbers. But in this case, the average of 85 and 85 is what? 85. So when you take the average, we add the middle two numbers, divide by 2, we get 85. Great. There are two modes here. 85 is a mode, and 100 is a mode because they're repeated. All right? If there was another number, hypothetically, if you had another grade which there were 3 grades of that, 3 copies of it, then the mode would be that grade. All right? So it's whatever number appears the most times, right? And any other numbers which also appear that most times, the grammar's not great, but I hope you get the idea. That's the mode. All right? Any questions? So your book has the habit of like writing this without indices. It just writes like sum over x, and if that makes sense to you, great. This is just the more complete way of writing that formula. So the way this notation works is it has an index I, and I runs from 1 to n. And in that case, that means we're reproducing x1, x2, x3, x4, da da da, all the way up to x10. In this example, it goes through 10. But okay, so if you guys have any questions, just jump in, all right? Three. Here's another example. Given data, here we go, given data minus 8.9, minus 2.4, 4.9, 9.7, 6.6, 8.5, and 4.9. And, you could, what do you want to, you could add a backstory to this data if you want, right? What data would be negative and positive? Maybe like, maybe this is the profit at a lemonade stand or something, right? So they lost $8.90 the first day. They lost $2.40 the second day. They made a profit of $4.90 the third day. then 97. I mean, whatever. You can make up a story. But the point is we can analyze data. All right. So sometimes I don't give a story corresponding to the data just so we can focus on the math of it. So that's the case here. So the first order of business is if you're given a data set which is not put in order, you have to put it in order to see like median and mode. Well, certainly to see median, maybe also to see mode, because as you put the data in order, you're going to repeat repeated entries, right? And so that might help you identify the mode and just the process of putting it in order. So this is already partly in order, like minus 8.9 is the smallest, the largest negative number here, right? Then minus 2.4, 4.9, 9.7, 6.6, 8.5. So some of these are out of order, right? So I'll put them in order down here. Minus 8.9, minus 2.4, 4.9. There's another 4.9 over here. 4.9, 4.9, 6.6, 8.5, and 9.7. So how many things are there? There's 7, right? This is odd. 7 is odd. So the median is just the middle number. The middle number here is 4.9, right? So 4.9 is the middle number. That's going to be the median. The mean, or the average, we add together all the numbers. I get 23.3. I divide by 7. I get 3.3286. Now, the problem's in your homework. It's pretty fussy, isn't it, about you following the rounding instructions. You've experienced this, yes? So I think it says round to the nearest tenth for these problems. So if we do that, we have 3.3286. Then I'm going to have 3.3 for the mean if I round to the nearest tenth, right? And do you guys, any questions about why 4.9 is the mode here? Does that make sense? Because it's the only number repeated, right? Okay. These aren't hard, right? This stuff is very easy as long as people actually explain to you what the silly words mean, right? Where this gets hard is if somebody asks you what the mode is and you have no earthly idea what mode means, right? That would be me in the past. Like, what are you talking about the mode? It's a mode. All right. What page are we on here? 4. Page 4. So here's another example. This one's a little bit more interesting. This is like one of your homework problems, all right? So here it goes. After 6 biology tests, all right, Brandon has a score of 80, a mean score of 80, an average of 80, right? What score does Brandon need on test 7? Man, they got a lot of tests in this class, you know? I don't want to, who wants to grade 7 tests in a semester? Not me. Goodness gracious, I do nothing but grade. To raise his average to 82. All right. So this problem requires some sort of symbolic thinking, all right? And so let me just walk through it here. So what I'm going to do is I'm going to say that x1 through x6 are the scores of the first 6 tests, right? We don't know what they are individually, right? But what we know is that their average is 80. So what we know is that x1 plus x2 plus x3 plus x4 plus x6, all divided by 6, must be equal to 80, right? Does that make sense? I hope. So since that's all equal to 80, we can do what? We can take this equation here and multiply by 6, and we get that the sum of the grades on the first 6 tests must be 480. Okay? Our goal is to find the value for the grade on the 7th test, so that when we add all the grades up and divide by 7, we get 82. Right? So if you write that out, it looks like this, right? x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 divided by 7 has to be equal to 82. But I know that all of these first 6 ones work out to 480, right? So what I have is that 480 plus the grade I don't know divided by 7 has to be equal to 82. Then I do algebra, right? Multiply both sides by 7 to get the 7 out of here. So 7 times 82 is 574. And then I subtract 480 from both sides. And that gives me x7 is 574 minus 480. which gives me 94. Now, if you can think of another way to work this problem where you get the same final answer, more power to you. Certainly there are other ways to think about this problem. You know? Like another way, I just thinking about it, here's another way you might have thought about the problem without doing algebra, right? Think about this. If you want 7 tests to have an average score of 82, what's the stupidest way to make that possible? Is to have a score of like 82 all 7 times, right? So like surely 7 times 82 is the total number of points earned. So like if you think about it, the total number of points earned being 574, that's kind of natural to think about, right? And then it's also easy to figure out that you've got 480 points that you've earned on the first 6 tests, if you think about that. So if you take 574 minus 480, that should be the number of points that you need to earn on the 7th test to get an average of 82. That's exactly what the algebra did. Yeah.
How did you get the 82 again?
That was given. The question asked, he wants to raise his average. That has to be given to you. Here's a more interesting question. What's the maximum average you could get on the 7th? If what if he makes 100 on the 7th test? Then what would his average be? What would that be? If you take 480 plus 100, you get 580. What's 580 divided by 7? So, whew, oh goodness, 82.85, so 82.9, this is really close to his theoretical maximum average. Like if he made a perfect score on test 7, he'd have an 82.9. What happens if he makes a 0 on test 7? What would his average be then? 480 divided by 7, right? So the lowest average he could conceivably get would be 68.6. So if he has the scenario if you're given the scenario you have here, if he makes a 0, his average after test 7 would be 68.6. If he makes 100, his average would be 82.9. You know? So basically, if you're going to ask this question with the setup that it has, you have to give a final average between 68.6 and 82.9. If I ask the students to find his grade on the 7th test so that his average is 95, that's not a tenable question, right? Unless the professor gives crazy bonus points on test 7, right? How does this problem work out for this class, by the way? So if you make a 50% on test 1, right, and a 90% on test 2, what percent grade do you need to make on the final to raise your average to 90? So I don't know if I told you guys this or not, but I will replace your first test grade with the final exam score if it's helpful. Did I tell you that? Okay, good. So what that means is that this calculation doesn't make sense for our course because I erase past grades for the final exam grade if it's helpful, right? So what that means is if you ace the final, you probably have an A in the course, assuming you've done homework and come to class, but anyway. Any questions? Let's go on. Yeah? Okay. Five. This is also like one of your homework problems. So you got a baseball player gets 94 hits from the first 274 times at bat. And then the second half of the season, he earns 64 hits from 282 times at bat, right? So he was doing a little better in the first half of the season than the second half, right? So we're asked a number of questions. Find the average hits in the first half season, find the average hits in the second half season, find the mean of the averages from part A and B, find the average hits for the whole season, and then part E, does the average of the averages match the average for the whole season? All right. Should the average of averages be the average? The answer is no, as it turns out. You can't just average averages to get averages. What I mean by that. So to find the average in the first half of the season, we just take 94. That's the number of hits in the first half, divided by the number of at-bats, which is 274, and we get 0.3431. All right? And then average 2, we take the number of bats in the second half of the season, 64, we divide by the number of at-bats, number of hits rather, 64 divided by number of at-bats in the second half, 282, we get 0.2270, approximately. Right? If you average 0.3431 and 0.2270, which is to say add these two numbers together, divide by 2, you get 0.2851. All right? And then what would the batting average be for the whole season? Well, you take the total number of hits and you divide by the total number of at-bats, right? And that you get 94 plus 64 divided by 274 plus 282, and that works out to about 0.2842. So is it close to the average of the averages? Yeah, it's kind of close, but it's not exactly equal, right? So there is a distinction between, say, if you know that the batting average of a player is 500 for the first half of the season, and it's 400 for the second half of the season, that does not necessarily mean that their overall average is 450, using the usual language of baseball. You have to, because the only way that would happen is if there were the same number of at bats in both the second and the first half of the season. Like if that happened, then the average of the average would be the average. But anyway, so no, they're close, but they're not equal. There's a difference. Any questions about this example? Baseball's a weird thing, right? You should be really happy if 2 out of 3 times you go to the bat, you fail, right? This is what the coach taught my son. He's like, baseball's all about disappointment, because 2 out of 3 times you go to the bat. If you're a great player, 2 out of 3 times you go to bat, you fail. It's a funny way to look at things. You would like for your batting average to be more than 30% on test 2, right? Yeah, I think so. All right, so 6. Here we go, another example. So given data, 11, 8, 2, 5, 17, 39, 52, and 42, find the mean, median, and mode of the data. So first order of business, put your data in order. So in this case, 2, 5, 8, 11, 17, 39, 42, and 52. All right, how many data points are there? There are 8. So, all right, so let's do it then. The average or the mean, add them all together, divide by 8. We get 176 over 8, which is equal to 22. Yep.
On the test, do you want us to write all that out, or could we just use a calculator?
I would encourage you to write it out if it's a short answer, because that way I can give you partial credit if you're wrong. But otherwise, you don't have to. Yeah. I can't really. It's hard for me to give partial credit to numbers for the short answer stuff, So there's that. But okay, so of course you could also summarize it more compactly too, right? You could do something like, you could write something like sum of x equals to 176, and then so sum of x divided by n is 176 over 8, which is equal to 22. I mean, you could write stuff like that
Okay.
if that's helpful to you
Okay.
as a kind of like summary comment. But okay, so the average is 22. No issue for rounding here. It works out to an exact number, right? It's kind of funny. The median, so this time we have to add the middle two numbers, which in this case are 11 and 17. So you add them, you divide by 2. 28 over 2 is 14. So the median was 14. Notice that the median doesn't have to be a number on the list, right? It's either the middle number or it's the average of the middle numbers. So, and the mode here, there is no mode. If you look at it, there's no number which is repeated more than once. So in this case, we say there is no mode. All right, we good? Let's move on. So that's section 13.1 for you. I haven't asked you any questions about weighted averages. All right? So I don't think I would. I'm skipping weighted averages in section 13.1 if you're keeping score. And so let's see here, 6, 7. Which, if I had the course to redesign over again, I might include weighted averages a second time through. I think that's actually a worthwhile concept to cover. I just missed it when I was making homework up. So if I haven't put it in the homework, I don't really want to put it on the test in this material. So anyway, here we go. So the next up is section 13.2. I think this is 13.2. Measures of dispersion. So in section 13.2, we talk about range, then what's called standard deviation, and then finally what's called the variance. All right? So let's start with range. The range of a set of data is the difference between the greatest and the least data values. This is a pretty easy idea, right? So you just look at all your data, you pick the biggest one, you pick the smallest one, you take the difference of those, that's your range. So let's see here. So suppose a crowded convenience store sells, not a really good name for a convenience store, but it would at least be honest, sells soda in the in-store fountain and sample size 2 ounces, mini 6 ounces, small 12 ounces, medium 16 ounces, large 20 ounces, and jumbo 44 ounces. My brother, he has this like bucket that he takes to whatever convenience store he has. They have this like deal, like monthly soda deal or something, where he just goes in and gets this like bucket of soda for some monthly fee. It's I don't know. It's an absurd amount of soda, but that would be like this. Actually, that's pretty. This jumbo is small compared to my brother's bucket cup, but anyway. So in this, obviously the biggest is jumbo, the smallest is the sample size that no one sells. I just made that up. And so 44 minus 2 is 42. That's the range for this data set. All right. The WNBA has players from age 15 to age 61, right? Then the range of ages for the WNBA would be 61 minus 15 equals 46. Did you know the WNBA has a 61-year-old player? You guys didn't know that? Oh, that's right, because you don't watch the WNBA, right? Just saying. So I could say whatever I wanted about the WNBA, and you'd have to believe it. So it's never too late to dunk on the WNBA. It's never too late. Oh man. Some of our greatest comedians have made a career of dunking on the WNBA. Let's see here. Oh, yowzers. Let's see here. I think we just made it to page 8. I'm sorry if I've offended you, since you're a deeply loyal WNBA fan. So next up, we talk about the standard deviation of a population. So here the text starts to get dodgy about language. It talks about population versus sample. So let me try to explain as best as I can. A population is really when you have the complete data set. All right? So if you have the totality of your data set, we call that a population. So for a population, the standard deviation is defined to be the sum of the squared differences between the data and your mean, all divided by n, and then you take the square root of all of that. All right? If, on the other hand, your data set is a partial representation of the totality of the data that's in question, right? If you're just taking a quote-unquote sample of the population, which is a partial data set, right? A sample, then we define the standard deviation, again, to be the sum of the squares of the differences between the data and the average. But for reasons that the textbook doesn't bother to explain, you divide by n minus 1. All right? And this is because this gives you the best predictions for inferential statistics if you study it more deeply. All right? So they claim. Again, I am not an expert, so I don't know how to explain that to you honestly, why there's an n minus 1 here as opposed to an n. I just will tell you that whenever you see the word sample, you need to divide by n minus 1. All right? I think most of the homework problems are on samples. Okay, so here is a sampled data set. See this word sampled? You got 2, a 4, a 7, a 12, and a 15 sampled from some larger data set, okay? So first of all, we'll calculate the average or the mean, same as before. Just add them together, divide by the number of them. So the average here is 40 divided by 5. The mean is 8 for this sample. All right? And then we'll calculate the sum of the differences between the data and the average, right? So you're adding together this quantity, whatever it is. It's getting bigger as you have more data points which are far away from the average, right? If you have more data points which are far away from the average, it means the data is kind of more spread out. So the standard deviation being large speaks to data being spread out more. That's the idea here. The larger the standard deviation, the more spread out the data. So we take 2 minus 8, 4 minus 8, 7 minus 8, 12 minus 8, 15 minus 8. So that's from this 2, this 4, this 7, this 12, this 15. See that? And you square them. So you get a minus 6 squared plus 4 minus 4 squared plus minus 1 squared plus 4 squared plus 7 squared. You're squaring, right? So the minus doesn't matter. The square eats the minus. You can ignore the minus in this calculation. It wouldn't hurt you, right? So this is 36 plus 16 plus 1 plus 16 plus 49. That works out to 118. All right? And then I want to calculate the standard deviation, which we call S here for the sample. We take the square root of the sum of the difference of the squares of the data, which we just calculated to be 118, and we divide that by n minus 1. Here n is equal to 5, so n minus 1 is 4. So we get 118 over 4. Let's calculate. What is 118 over 4? So do you guys like time travel? So S squared equals to 118 over 4 equal to, 29.5, thank you, is the variance. We haven't explained that yet, right? But I'll define that in like the next slide, okay? So, but anyway, you take the square root of that, you get 5.431. This is the standard deviation. So, all right. I would encourage you guys to look at example 3 in section 13.2. I think that's a nice example. I think we might have time to look at it today. Let's see here. So here's example 3. Playing with fire here. So here's example 3 from the text. Here they give us a consumer group has tested a sample of 8 size D batteries from 3 companies, and the results of the tests are shown in the following table. According to these tests, which company produces batteries for which the values representing hours of constant use have the smallest deviation? So you've got these 3 samples, right? This list of hours of constant use per battery. This list, ever so bright, dependable, beacon. Anyway, so the average, it turns out that they have concocted these data sets so that the mean of each one of them is 7. So the average battery life for each is 7. And you can calculate the, wait a minute. Oh, 8, right? There's 1, 2, 3, 4, 5, 6, 7, 8. N is equal to 8 here, so dividing by n minus 1 is dividing by 7. So they calculate the standard deviation for the first list is about 1.328 hours. The standard deviation for the second list is about 0.7198 hours. And the standard deviation for the third list is 0.877 hours. So what does that show us? That shows us that the dependable batteries have the most, have the closest data. They have the closest number of dependable hours of battery use, right? On the average, they're all coming out to 7 hours of battery use, right? But it's more likely that if you get the dependable battery, you're actually going to get 7 hours of use. Now, on the other hand, the ever so bright batteries are kind of nice. I mean, in principle, you could have an ever so bright battery last you 9.3 hours, which is kind of nice. But you don't know that's going to happen, right? You could have also one that lets out on you an hour and 1.1 hours early, which would be bad, right? In contrast, the dependable, notice how that the data is more closely grouped around 7, and that's why the standard deviation is calculated to be smaller. So when the data is more spread out, the standard deviation is bigger. When the data is more tightly grouped, the standard deviation is smaller. Okay, enough about that example. And again, that's
The dependable battery was the answer because it was the smallest number?
Let's see here. It said the question was, which company produces batteries for which the values representing hours of constant use have the smallest standard deviation? So the question was, which standard deviation was smallest? The answer was yeah. So yeah, the dependable batteries. Okay, so let's talk about variance. What page am I on here? 8. So I've already done an example of variance for you guys because, listen, anytime you calculate standard deviation, I think usually if you're doing the calculation by hand, you will calculate the variance on the way to calculating the standard deviation because the variance is just the square of the standard deviation. So usually you calculate the variance, then you take the square root. That's how you calculate the standard deviation, yeah? So they're very related, these two numbers, okay? But so the variance is just the square of the standard deviation, which is given by this formula here. And that's, of course, the variation of a population, right, the total data set. The variance of a sample is the square of the standard deviation for a sample, which, again, the difference is that we divide by n minus 1 rather than n for a sample of n, okay? For reasons of magical statistics. Yes?
I'm a little confused on the notation, the weird
the weird E, the xi, yes. The weird E, let's see here. So, this notation, the weird E, right? So if I have I equals, say, 3 to 7 of, let's say, A sub I, what that means is we start at 3, and then we add all the way until we get to the top thing. So this is read sum of A sub I from I equals 1 to I equals to 7. So this is quote-unquote summation notation. That's the weird E.
So what's the I?
I is, well, here I is usually called the index. It's an index. It's just a, you know, Charity, is it? You're X1. What's your name? You're no longer Allison. You're now X2. I'm going to jump over to you. Who asked the question? What was your name?
Lauren.
Lauren, excuse me. But you're no longer Lauren. You're now X3. So like, this is just labels for the data. Although I really shouldn't label you guys, but like X1, X2. You're not just a number, right? You're like a person and stuff. So, but the X1, X2, those are just generic labels for the data that we're talking about. So that was like X1. X sub I, that's the ith data point. So I is the index. It's a system, it's just a system of enumerating, a system of labeling. Other things I can tell you about, I know because this is, I think I see where you're going with these questions. Mu is the Greek letter mu, which is read like a cat. Sort of like mew. No, wait a minute. That doesn't work. Do you have cats say mew? They say meow. Rats.
Kind of like a cow.
Like a cow. That's moo. That's still not right. What says mew? A Greek says mew. So it's the Greek letter mu. And then this guy is actually sigma, which is somewhat ironical because this funny looking E we were talking about is actually capital sigma because it's for sum. So anyway, so sigma for us is, we use that for standard deviation. Okay, let me get back to my exam, page 9. Did I answer your questions?
Yes, except what are those next two symbols?
Which one?
The ones that mu and sigma. What do they mean?
Mu is the standard, oh, excuse me, my bad. Mu is the mean, or the average, right? And sigma is the standard deviation. Sigma squared is the variance, all right? Now that's for a population. For a sample, just to make things confusing, we use different letters. We use x bar for the average of a sample, all right? And the x bar is defined by dividing by 1 over n. It's still calculated the same way we calculated the average for the population. But what's different is that the standard deviation for the sample, we divide by 1 over n minus 1 here, whereas there's a 1 over n for the standard deviation of the population. And then the variance for a sample is again the square of the standard deviation. Are we good? Oh, okay. So, I made up this example because I'm an idiot. I'm an idiot because it took me forever to calculate. The grades in a class are 40, 51, 49, 65, 65, 67, 68, 70, 70, 71, 73, 80, 84, 88, 92, and 99. All right? And then I said find the, so that's not a sample. That is the whole population. That's the whole data set. So we're going to calculate sigma and sigma squared and the mean here. And so the mean I start out with, I add all the grades up, I divide by 16. I got 71.43 approximately for the mean, right? And then to calculate the variance, I have to say 1 over 16 times the sums of the differences of the grades with the average grade squared. So 40 minus 71.43 squared plus 51 minus 71.43 squared plus dot, 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 all the way to 99 minus 71.43 squared, right? So the grades which are absolutely farthest from your average are making this variance the biggest, those are which are most deeply contributing to the variance, right? Outliers, if you will increase the variance by a lot. So if you want to manipulate your data and you want to convince people that the story is better than it is, it's very convenient to find a reason as a business or corporation, government, whatever, to just throw out some quote-unquote outliers for whatever made-up reasons. See, because if you do that, if you just throw out a couple of these outliers, all of a sudden you've like made your data much more tightly packed, which might have a good meaning for the outcome you're looking to describe. So you have to be very, very suspicious of statistics because the devil's in the details, and like just excluding certain data points for made-up reasons is a very nice way to manipulate the statistics to get what you want. Anyway, so the sums of the squares here are 988.3, 417.4 all the way down to 760.1 on the other side of things. You add all those up, you get 3358.3. Divide by 16, I get 209.9 for my variance. Then the standard deviation is the square root of that, which is 14.5. There we go. Now I can be alone with my thoughts again. Okay, so any questions about this? I mean, so I think the first thing I would say here is I really don't want to calculate this by hand, right? Is there a better way to do this kind of calculation? What do you think, guys? Is there a better way? What would the better way be? Everyone's top-hatted, right? Okay. Let's see here. So let's try out that one we just did. All right. But let's use, you guys had university, what was it? 101? Did they make you guys do Excel in there? They didn't? Was that Research 101? Research 201? Is there some required class that you've been forced to do Excel in?
Yeah, it's information technology.
Information technology. Hey, that seems like, I guess the label's not too bad there, is it? All right, so let's take Excel for a spin here. Now this will help you with your homework, right? What about your test? Not so much, right? There's like no open computer part of the test, is there? No. You don't want that either. That would make this class much worse than it is. So what were my grades? What did I have? I had 40, 51, 59, 65, 66, 67,